Welcome, this is Professor Ridge, and today's lesson 6.2 Graphs of Exponential Functions. And our first learning objective, graph exponential functions. Alright, let's look at the graph of something in the form of f of x equals b to the x, where b is greater than 1. So let's just start out with, say, f of x equals base 2 to the x. So again, remember, exponential functions, the exponent is the independent variable, right? The input value goes in the exponent. So if we do 0, 2 to the 0 is 1. We do 1, 2 to the first is 2. 2 squared is 4. 2 cubed is 8. And then if we do to negative 1, 2 to the negative 1, remember negative exponent is 1 over. And then if we do negative 2 to the negative 2 is 1 over 2 squared, which is 1/4. And then we get 1/8, 1/16, 1/32. Okay, so let's plot these. So 0, 1. 1, 2, back here, 2, 4, 3 cubed, or 3, and then you're going to put 3 in for the x, so 2 cubed is 8. So we plot 3, 8. Going the other way, we get 1/2, negative 1, 1/2, negative 2, 1/4. If we did negative 3, we get 1/8, 1/16, 1/32, so on. And then we have I do terrible on these on this board that I have here. But anyway, we get this kind of curve, which is exponential function. Alright, so that's your basic exponential function, and if we change this to 3, it's going to have a similar shape. So the characteristics that we should know is that we have an asymptote, x equals 0, or y equals 0 is a horizontal asymptote. And then this curve is our exponential growth curve, and then our domain is all real numbers. And the range is just the positive values, so it'll never equal 0. Oh, so it's going to, oh yeah, that was right. It doesn't equal 0, so we use a parenthesis. Okay, so those characteristics. Now, so if b is greater than 1, it's going to have this shape. It's going to go as the base gets bigger, larger. So if that's 3, 4, 5, this will just basically have the same shape, this exponential growth curve, but it'll be steeper. So basically, if you just learn to do these 3 spots, 0, 1, and negative 1, and then it's just going to, any base to the 0 will be 1. Anything to the 1, it's itself. Anything to the negative 1 would be 1 over itself. So our shape is going to be this exponential growth curve. So whatever b is, we go 0, 1, 1, whatever b is. So if it's 2, 3, 4, whatever, we're going to go 1 to whatever the base is, and then 1 over the base. And it's going to have that exponential growth curve, basically like this. Okay, so let's look at Desmos, and I can show you that real time. Okay, so here's on Desmos, y equals 2 to the x, the one we just did by hand. So 0, 1, 1, 2 to the 1 is 2, 2 squared is 4. So the x is 2, and then it's 2 to the x, right? 2 to the third was 8. And then if we do negative 1, is 2 to the negative 1 is 1/2, or 0.5. to the negative 2 is 1/4, which is 0.25. And then if we do to the negative 3 would be 0.125 or 1/8. All right, so you see that now. The point I was saying now is b changes. If b is greater than 1, it's going to have this basic, what we call exponential growth curve. So as we change b, okay, so that's the 2, the red one. Now, the blue one is, I'm going to change the base to show you. So if b is 3, let's go to 3. So this is 3 to the x. So 0, 1, and then it's going to be 1, 3 to the 1, which is just 3. And then 3 squared would be 9, right? But it has the same basic, what we call exponential growth curve. And then negative 1, 3 to the negative 1 is 1/3, which is 0.333 forever. And then this is 1/9, 1/27. Okay. So, and then you can see, so as b gets bigger, that curve gets steeper. So if I go to 5, b is 5. B to the first power, which is 5. 5 to the first power would be 5. 5 to the second power, you can see would be 25. So it's way up off the chart here. Right, I would have to go all the way up to here, 25. But it has that basic curve. And notice on the right side of the y-axis, it's steeper. It's getting bigger quicker. And on the left side, it's approaching 0 faster. So it's going down to 0 quicker than the basic 2 one. Okay, so you can see as you change the base, it has that same basic shape. Again, the exponential growth curve. And then when you get lower than 2, it's going to be a little less steep. And then, of course, if it's 1, you just get a horizontal line, which is not an exponential growth curve. So b can't be 1 to be considered an exponential equation. Okay, so b has to be a positive number other than 1. All right, so let's choose a b to be between 0 and 1. So let's say f of x is equal to 1/2 to the x. So if we have x, f of x, or you can write y, doesn't matter. So anything to the 0, so 1/2 to the 0 is 1. 1/2 to the 1, oops. 1/2 to the first is 1/2. 1/2 squared is 1/4. 1/2 cubed is 1/8. And then if we do negative 1, now remember, there's two ways to think of negative 1 exponent. You could think of it as 1/2 to the negative 1. You can think of it as 1 over, or you can think of it as reciprocal. So the reciprocal of 1/2 is 2. So we're going to flip it over and then take the power. That's another way to think of it. So 1/2 to the negative 2, that would be 2 over 1, which is 2, and then square it, which is 4. So we get 0, 1, 1, 1/2, 2, 1/4, 3, 1/8, and then going to the negative, we get negative 1, 2, negative 2, 4, and then if I did 3, that'd be 8. So this basically flips the graph around. It's a reflection through the line y equals, or the y-axis, sorry. I'm trying to graph and talk at the same time. Sometimes that doesn't work very well. Okay, so there we go. So that's what we call an exponential decay. So basically, if we have f of x equals b to the x, and b is between 0 and 1, okay, we're going to get an exponential decay curve. Okay, so it's going to basically you're going to do the 3, 0, 1, and -1. B to the 0 is 1. B to the first is B. B to the -1 is the reciprocal B. But what you got to remember now is that B is between 0 and 1. So B is going to be somewhere down here between 0 and 1. Oh, I messed up. So if we get 0, 1, 1b, and then 1 over b is going to be up there somewhere. Okay, my table got in the way, but hopefully you get the idea. So it's going to have that shape, exponential decay, and we can look onto Desmos again. So if we take this, and now we're going to change b to be between 0 and 1. 0 and 1. So like 1/2, which is 0.5. So at 0 it doesn't make sense, right? So that's why we don't have the graph here. But then let's change this to 1/2. 1/2. Okay, and you can see that. We'll change this to 0.5, which is 1/2. And then you can get the points that we just did. 0, 1, 1, 1/2, 1, 1/4, 1, 1/8, -1, 2. What did I do? Anyway, you got the idea. Hopefully. There we go. Okay. And then you can see as we change the B, right? Same idea. So as it gets closer to 1, it's going to get closer to that horizontal line. At 1, it's the horizontal line. So it flips around the x-axis. I mean the y-axis, sorry. Okay, so you can kind of see that. So they all have that basic shape. So once you understand that, you can just do 0, 1, -1. If it's small enough, you could do 2 and -2 as well. And then if fits 3 and -3. But typically, just to know the shape, do 0, 1, -1. Start with those. I'm talking about the x's, 0, 1, -1. And then if you can fit 2 and -2, do those as well. If you can fit 3 and -3, again, you can do those as well. Okay, and again, it's still some characteristics or horizontal asymptote's going to be y equals 0. And our domain's still going to be all real numbers. And then our range is still going to be the positive integers, or positive real numbers, sorry. Oops. It has to be a parenthesis. Okay. Alright, so the book has a nice graphic, summarizes what we just went over. So exponential function of the form f of x equals b to the x. B is greater than 0, but not 1. Okay, it's a one-to-one function. We didn't talk about that, but you can see it passes the horizontal line test, and as well as the vertical line test to be a function. Horizontal, one-to-one. They both have the horizontal asymptote, y equals 0. So this one, if b is greater than 1, it's approaching 0 on the left end, and it's approaching 0 on the right end if b is between 0 and 1. Okay? Domain and range, negative infinity, infinity for the domain. Range is 0 to infinity. Neither of them have x-intercept, right? It's never going to equal 0. The y-intercept is 0, 1. So it doesn't matter what b is, it's always going to cross at 0, 1 on the y-axis. And then If b is greater than 1, this is an increasing function, right? It's exponential growth. And if b is less than 1, it's decay. It's a decreasing function. So now we can add these to our basic toolkit functions and use all our transformations that we learned earlier in the text to transform this. So we're going to start this. They're calling it the parent function. So I'm just going to transform these to graph any other exponential function. Okay, so let's try example 1 here. Sketch a graph of f of x equals 0.25 to the x, which is also the same thing as 1/4, right? 0.25 is 1/4. So if you want to write it that way, that's fine. So again, remember 0, 1, -1. So anything to the 0, 0.25 to the 0 is 1. Anything to the first power is itself, so this would be 0.25. Anything to the -1 power is 1 over. Now if you know that 0.25 is 1/4, then it's the reciprocal 1/4, which is just 4. And then if we can fit 2 and -2, they're 2.25 squared is 0.0625. And then if I did -2, that would be 16, right? Because it's square of this one. So it would be 16. And if you don't believe me, punch it in a calculator, you'll get 16. Okay, so 0, 1, 1.25 or 1/4 point, right? So it's going to 0 real quick. And then -1 is 4, -2 is off the chart here. So, and then we do that exponential decay curve. I'm not good with this board that I'm using because I have to look at the screen while I'm, instead of look at what I'm writing. Let me try that again. Okay, so there we go. Right? Pretty much I did my best. So hopefully you got the idea. So exponential decay. Oh, then it says state the domain. Domain is all real numbers. Range is 0 to infinity. So remember, range is if you squash it, take all the y values for every point. So it's going down to 0, but not 0. And then it goes all the way up to infinity. So 0 to infinity. And then asymptote. So it's the y-axis. Not the y-axis. The x-axis, which is y equals 0. Okay, so now we're ready to graph exponential functions using transformations. Okay, so graphing using transformations, shift the parent function. So basically, we have b to the x plus c. So this plus c is going to shift it left to right. And then the plus d, that's going to shift it up, down. Okay, so vertically, you're going to shift it vertically d units, and it's the straight. And remember, when you're up inside with the variable, you do the opposite. So you're going to do horizontal c units in the opposite direction of c. Okay, that's the thing to remember, because if you remember back when we did the transformations, we typically had like f of x, or wait, so if this was our parent function and then we wanted to graph g of x, which was a f of x minus c plus, well, not c, we did h and k, right? So this was the opposite because of the minus here, right? So that's the idea. So the plus c, you're going to do minus c. All right, and then the y-intercept's going to get shifted. The horizontal asymptote's going to get shifted. And the range is going to get shifted, right, by d units. and the domain will remain unchanged because it's from the domain's all real numbers. So even if you shift it side to side, you're still going to have all real numbers. All right, let's look at example 2, graphing a shift of an exponential function. So graph f of x is equal to 2 to the x plus 1 minus 3. State the domain, range, and the asymptote. So my parent function is just what I call my base function. It's just y equals 2 to the x. So if I do x, y, I'm going to do 0, 2 to the 0 is 1. 2 to the 1 is 2, and since it's 2, I'm going to go ahead and go to 3. 2 squared is 4. 2 cubed is 8, because that's small enough. And then negative 1, so 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4, and 2 to the negative 3 is 1/8. Okay, and then you'll be able to generate these numbers quickly with a little practice. Now we're going to shift it negative 1, x. So what I do is I draw on my graph, I draw what I call a pretend x and y axis. So, and we're going to go down 3. So I need to change my axis here. I'm going to go down 3. And I'm shifting it to the left one. Well, that I have enough room. I can make it a little bigger that way. So this is shifting it to the left one because you go minus 1. Remember the opposite. So plus 1, you do the opposite. Make it a different color. And then minus 3 for this one. Okay, so this is how I'm shifting. So this is going to be my horizontal asymptote. It got shifted down 3. So y equals negative 3. That's my horizontal asymptote. And I'm going to pretend that this is the origin and plot my parent function counting from here. So 0. So basically, I would think of this as 0, 0, and this would be 1, 2, 3, 4, 5, 6, 7, 8, counting from my pretend origin, which is negative 1, negative 3. And then this would be negative 1, negative 2, negative 3, 1, 2, 3. So typically I don't write that, but I'm just trying to show you what's going on in my mind here. So I'm going to plot these points counting from what I call the pretend origin, which is the shifts, right? So shift left 1 and down 3. So I'm going to take the parent function y equals 2 to the x, shift it left 1 down 3, so I made my pretend origin, and now just plot these points pretending the origin was right here. So 0, 1, go back to the pretend origin, 1, 2, back to the pretend origin, 2, 4, 3, 8, and then negative 1, 1/2, 1/4, 1/8, and then draw my graph. Okay, so we get that exponential growth curve there. And let's see, state the domain. So the domain's still all real numbers. The range, okay, the range got shifted. We shifted it down 3, so it's from negative 3 to infinity. And it's open parenthesis because it doesn't hit. That's a horizontal asymptote, and it never hits it in this case. And then the asymptote is y equals negative 3. Okay, so graphing, approximate the solution of an exponential equation. Solve 42 equals 1.2 times 5 to the x plus 2.8 2.8 graphically. Round to the nearest thousand. So the book shows you the keystrokes for using a TI graphing calculator, where you could just use Desmos. So let's get Desmos up. So the technique is basically we're going to graph two lines. We're going to graph y equals 42. So if we graph this, y equals 42 is a horizontal line. And then 5 to the x times 1.2. The 1.2 would vertically stretch the base graph. And then the plus 0.8, 2.8 would shift it up 2.8. So it's gonna be some kind of graph like this, and that intersection point would be the solution to this equation. So we got to figure out what the x-coordinate is at that point. So we're just going to go to Desmos and type in y equals 42. We're going to type in y equals 1.25 to the x plus 2.8, and we're going to click on that button, and it'll show us the x and the y coordinate. The y coordinate is going to be 42 because it's on that line, and then whatever the x coordinate is, that's the solution to this equation, the approximate solution. Okay, so here's Desmos. Type in y equals 42. I turned it off because I wanted you to see what's going on. So you can scroll out, and you see that's what's nice about Desmos too. It's very dynamic. And then there's the exponential curve, like I showed you, what I expected, exponential growth. And then you're going to look for where they intersect, and you just click on it. And then see the y coordinates 42 for both graphs, the x coordinates 2.166. They wanted us to estimate 3 places. So that's our solution to this equation. So x equals 2.166, or I should say about equals. And you can see, and you can test if you put in 1.2 times 5 to the 2.166 plus 2.8, you're going to get something really close to 42. All right, so graphing a stretch or compression. So if you recall from our transformations, if f of x, if y equals f of x, y equals a times f of x. If the absolute value of a is greater than 1, that's a stretch, right? So this one, if we took f of x as 2 to the x and we multiply it by 3, that's going to give us a vertical stretch. So you take all the y coordinates and times it by 3. So if we're here at 2, if we're here at x, y, we have 2 to the x. So 2 to the 0 is 1. 2 squared is 4. 2, oops, this should have been 2, 1 is 2. 2 squared is 4. Sorry. Okay, so then we're going to multiply those by 3. So this is going to be 0, 3, which is right here, and then 1, 2 to the 1 is 2, and then 2 times 3 would get us to 6. So it's going to stretch it. And if we did 2, 4, and then the 4 times 3, this one will go way up to 12. So this will go way up there. All right, so that's a stretch if a is greater than 1. And then I'm saying absolute value because if a is like negative 3, you do the 3 for the stretch, and the negative will flip it over, which that's going to be our next slide or two from now. Now, if a is if absolute value of a is between 0 and 1, that's a compression. So if a is 1/3 in this case, we're going to take all these values. 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, and then you multiply it by a, in this case is 1/3. So 1 times 1/3 is right there, and then 1, 2, and then we times it by, so that's a compression, so it's pushing it down. So 2 times 1/3 is 2/3, and then 2, 4 times 1/3 would be 4/3, which is right there. 1 and 1/3, right? Okay, so that's a compression. All right, so here's a summary of what we just talked about. So for any factor a greater than 0, the function f of x equals a times b to the x. It's stretched vertically by a factor of a if it's greater than 1, if the absolute value is greater than 1. Again, if a is, here we're talking a is positive, but in general, if it's positive or negative, doesn't matter. It's the absolute value of that will stretch it or compress it, and then the negative part flips it over the x-axis. Okay? So it's compressed if it's less than 1, so between 0 and 1. And if the y-intercept's going to move, instead of being 0, 1, it'll be 0, and then 1 times a would be whatever a is. And the horizontal asymptote's going to remain unchanged. Range is going to remain unchanged, provided a is positive. And then the domain is going to remain unchanged, right? So all those stay the same. Okay, so let's try this one. 0, let's see, example 4, sketch a graph f of x equals 4 times 1/2 to the x. So we're going to start with the parent function being 0, 1, since this is 1/2, I'm going to go ahead and do 2. So we got 1/2 to the, oh, that should be x. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. 1/2 squared is 1/4. 1/2 to the -1 is 2. 1/2 -2 is 4. And then I'm going to times it by a. Y equals 4 times 1/2 to the x. I'm going to times this by 4. So when I graph, this is going to get me 0, 4. 1, 1/2 times 4 is 2. 1/4 times 4 is 1. And then this one is going to be -1, 8, -2, 16. So let's see, 0, 4, 1, 2, 2, 1. And if I did 3, it'd be 1/8, which would be 1/2. Yeah, 1/8 times 4 is 1/2, so on. And then let's see, -1 would be 8, and -2 would be off my graph here. Oops. So let's do that. There we go. Okay, so that's an exponential decay. And then the domain is going to remain unchanged. So -infinity to infinity, all real numbers. Range remains unchanged. So 0 to infinity. And the horizontal asymptote remains unchanged. Y equals 0. Okay, so graphing reflections. So reflections about the x-axis. So if we times this by -1, that's going to take it and flip it over the x-axis. So if we did f of x, I should have wrote this little. So this is the same thing as -1 times 2 to the x, just to emphasize the -1. A is -1, so it flips it over the x-axis. So note that -2 to the x is not -2 to the x, right? So if you don't have parentheses, this one is what I wrote down here, -1 times 2 to the x. So you do 2 to the x first, and then times it by -1. This one is negative 2 to the x, which will not be an exponential function because a has to be a positive number. So remember, be careful about that. Now this one, if you put the negative up in the exponent, it flips it about the y-axis. So, and then also note that 2 to the negative x is equal to 2 to the negative 1 times x using exponent rules, and then 2 to the negative 1 is the same thing as 1/2. So 2 to the negative x is the same thing as 1/2 to the x, and you get this exponential decay. And notice that's a reflection about the y-axis. Okay, so those are a couple things to note about that. Reflection is the parent function f of x equals b to the x. So kind of summary what we just talked about. The function f of x equals negative b to the x reflects the parent function about the y-axis. Oh, I'm sorry, about the x-axis. Okay, reflects about the x-axis. So it's going to flip it upside down. So x-axis. So this, if our graph did that, it'd flip over. It'd be that one. Okay, and then has a y-intercept of 0, -1. Now the range, instead of being from 0 to infinity, it's going to be negative infinity to 0 because it flipped over the x-axis. Horizontal asymptote doesn't change, and domain doesn't change. F of x equals b to the x reflects the parent function about the y-axis. Okay, so that was this one, reflects it about the, so if we have y equals 2 to the x, flips it about the y-axis, which is the red one there. Okay, it has a y-intercept 0, 1, so that doesn't change. That asymptote y equals 0 doesn't change. The range doesn't change, and the domain. So all that stays the same. It just flips, oops, it just flips about the y-axis. Okay. Okay, find and graph the equation for a function g of x that reflects f of x equals 1/4 x about the x-axis. So we want to flip it about the x-axis. So we want to flip it. So let's see. If we have y equals 1/4 to the x, we'll just do 0, 1, -1. 1/4 to the 0 is 1. 1/4 to the 1 is 1/4. And then reciprocal. So this is my parent function, 0, 1. Okay, so we have 0, 1, 1, 4, 2/16 off, and then, oh no, 0, 1, 1, 1/4. I messed up there. Then this would be 1/16. That other one was going to be the reflection. Okay, so we get, this is, again, we call this an exponential decay. And then we're going to flip it about the x-axis. Right? So what we want to do, it's actually going to do it this way. We're going to flip it upside down. So this point, all these points are going to become times -1. So g of x is going to be -1/4 x. So we're going to multiply all these by -1 to get the g of x. So it'll be 0, -1, 1, -1/4, and then this will be 1/16, and then -1, -4, and it flips it upside down. So we get this kind of curve. Okay. And state the domain and range. So the domain is all real numbers. Range, now it's on the bottom side, so that's from negative infinity to 0. And then asymptote remains unchanged. So horizontal asymptote, y equals 0. All right, here's a summary of all the transformations that we went over. So translation is, let's see, parent function is y equals b to the x. The a, that's going to be stretch horizontal, let's see, that's the stretch vertically by a factor of a if it's greater than 0, compressed if it's between 0 and 1. The plus c shifts it to the left if it's positive, and to the right if it's negative, right? So you do the opposite sign. And then d shifts it vertically d units. So if d is positive, shifts it up. If it's negative, it shifts it down. And then if a is a negative number, it flips it over. So note the order note the order of the shifts, transformations, reflections follow order operations. So typically you're going to do the C first, this one first, then the stretching, compressing, the reflecting, and then the shifting up and down. Okay? Let's take a look at example 6, writing a function from a description. Write the equation for the function described below. Give the horizontal asymptote, domain, and range. So f of x equals e to the x is vertically stretched by a factor of 2. So remember, that's this a here. So we're going to say g of x is going to be 2 times e to the x, then reflected across the y-axis. So that's going to change the x to negative x. And then shift it up 4 units. So that's the plus 4 outside here. Okay, and then that's pretty much it. So now we want to, let's see, what's the horizontal asymptote? So we shifted it up 4, so the horizontal asymptote will be horizontal asymptote. Instead of y equals 0, it'll be y equals 4. The domain, let's see, the domain's going to remain unchanged. So your domain's going to be negative infinity to infinity. And then the range, well, it got shifted up 4, so it's going to be, and the negative flipped it about the y-axis. So e to the x looks like that. So we're doing e to the negative x. The 2 is stretching it, and then we lifted it up 4. So the domain's going to be from the horizontal asymptote to infinity. So it would be from 4 to infinity. And that's it. And then it looks like, yep, that brings us to the end of the lesson. So again, practice, practice, practice. Go to the end of the exercise, end of the section, not this exercise, end of the section, and do all the odd exercises. Do as many as you can. And if you have time, do some of the even ones as well. All right, have a great day and see you next time.